Imagine, just for a second, that you're the lead engineer tasked with building the backend system for Netflix. You've got to store absolutely everything. We're talking a complete record of what every single user has watched, the exact second they paused a movie, what device they streamed it on, their specific ratings, and all of their constantly evolving preferences. And here's the kicker. You have to do this for over 300 million users. You have to handle this data at a massive, truly global scale, while simultaneously providing blazing fast reads so the user interface never ever lags. If you try to build this using your standard run-of-the-mill relational database, the system is simply going to collapse under its own weight. The sheer volume of concurrent writes and reads would just create a completely crippling bottleneck. Okay, let's dive into this, because the answer to that massive system-breaking engineering challenge is the wide column database. Throughout this explainer, we're going deep into how these databases are actually designed, how their underlying architecture handles such ridiculous scale, and why they might just be the exact tool you need for your next massive application. Here is our roadmap for this explainer. First, we'll answer what is wide column. Then we'll look at the architecture, followed by disk storage, real-world scale, and finally, we'll wrap up with the trade-offs. Section 1. What is wide column? Beyond the traditional table. Let's immediately clear up a really common misconception right off the bat. A wide column database is not, I repeat, is not, just a standard SQL table that happens to have a ton of columns. In fact, if you look at the academic literature, you're going to see it defined as a sparse, distributed, multidimensional sorted map. Now I know that is a bit of a mouthful, so let's break it down. Sparse simply means that not every row needs to have every single column. Distributed means the data doesn't just live on one machine, it spans across many. Multidimensional means the data is indexed by multiple keys. And finally, sorted map means the data is physically sorted on the disk for incredibly fast access. Some of the big hitters in this space include Apache Cassandra, Google Bigtable, and ScyllaDB. To really visualize this, compare it to a rigid relational database. In standard SQL, if your table has 50 columns, every single row stores 50 values. Even if a user hasn't provided data for 40 of those columns, the database still has to store null values, which takes up space and structure. But in a wide column database, it's sparse. Row 1 might only have 3 columns. Row 2 might have 10,000 columns. Crucially, only the columns that actually exist for that specific row are stored. Literally zero wasted space for empty data. Section 2. The architecture. Modeling the data. Let's move to and see how this builds, using Apache Cassandra as our primary reference today, since it's pretty much the most widely used system in this space. Wide column stores organize data around a few core concepts. First up is the keyspace. Think of this as your top-level namespace, kind of like a database in SQL. Inside that, you have your tables. But right here is where it gets super interesting. Every row is identified by a partition key. Listen, this is the single most important design decision you will make, because the partition key determines exactly where on the cluster your data physically lives. Then you have clustering columns. Within a partition, rows are physically sorted by these clustering columns, and that is exactly what enables those blazing fast-range queries. Finally, you have the columns themselves, representing your actual data. And all of this data is distributed using something called a ring architecture. Cassandra uses consistent hashing, where each node in your cluster owns a specific range of a hash space. When you write data, your partition key is hashed, and that underlying math dictates exactly which node stores the data. It's also automatically replicated to multiple nodes for safety. Because of this really elegant mathematical distribution, there is no single master node. Every single node can accept both reads and writes. This masterless architecture means there is, for all intents and purposes, no single point of failure. Section 3. Disk storage. How data physically lives. But how does this actually work at the bare metal hardware level? This is the part most tutorials just completely skip over. But as engineers, understanding how data physically lives on disk is where the true beauty of this entire system reveals itself. When you write to Cassandra, it handles the data with a brilliant, highly optimized sequence. First, it simply appends the write to a commit log on the physical disk for durability, just ensuring you can recover if there's a crash. At the exact same time, it writes to an in-memory structure in the RAM called a MemTable. Now, because the commit log is just sequential appending, meaning no random seeking back and forth across the hard drive, it is incredibly fast. Once that MemTable in the RAM fills up, It flushes the data to the disk as an immutable S-table, or sorted string table. Over time, you're going to get a lot of these S-tables. So the system runs a background process called compaction to quietly merge them, sort the rows, and clean up any deleted data. This specific write path is exactly why Cassandra can casually sustain 1 million writes per second on pretty modest hardware. Now, what's really interesting here is a secret weapon Cassandra uses before it even touches the physical disk to look for your data, the Bloom filter. This is a probabilistic data structure that lives purely in memory. In O1 time, the Bloom filter can tell the database whether a key definitely does not exist in an SS table. By doing this, Cassandra entirely avoids wasting precious time and disk I/O searching for data that isn't even there. Section 4, Real-World Scale, Wide Column in Action. All right, so we have this masterless hash ring, sequential writes, and Bloom filters. Let's make this concrete by looking at how the absolute biggest tech companies in the world actually leverage these mechanics. And this brilliantly illustrates the sheer power of choosing the right keys. Take Discord, for example. They store over 4 billion messages. Because users usually just want to see the last 50 messages in a chat, Discord uses the channel ID as the partition key and time as the clustering key. This means all messages for a specific channel live on the exact same physical node, and they're already sorted by time. Fetching the last 50 messages is just one quick sequential disk read. Netflix uses the user ID as the partition key to track streaming events. And for smart city IoT sensors that are blasting out data every single second, they use a compound key combining the sensor ID with a date bucket. That ensures a single sensor's partition doesn't just grow infinitely over years of data collection. Section 5, Trade-offs. When to use and when to avoid. Look, of course there is no such thing as a perfect database. Every single architectural decision comes with a cost, so it's absolutely crucial to understand when to avoid this technology entirely. If you bring a traditional relational database mindset to a wide column store, you are going to have a really bad time. There are absolutely no complex joins here. All the data is denormalized. Furthermore, you cannot just write your data and figure out how you're going to query it later. Your query patterns must be pre-designed, and you build your schema entirely around those specific queries. You also don't get full multi-table ACID transactions like you do in standard SQL. And by default, you're dealing with eventual consistency, meaning if you write a piece of data, a read just a millisecond later might be slightly stale. If you're building a banking app where every cent must perfectly align in real time, this database will fight you every step of the way. On top of all that, managing things like compaction and partition sizes requires some pretty high operational expertise. So the crucial point is that you accept those specific trade-offs to gain some absolutely unparalleled advantages in scale. You get linear horizontal scalability. If you need 10 times the throughput, you literally just add 10 times the nodes. No complex sharding logic required. You get incredible high availability, where your system can survive multiple nodes physically catching on fire without a single second of downtime. You get unmatched write throughput that's just perfect for event logging and time series data, and you get built-in geographic distribution, so your data can replicate across the globe automatically. A wide column database is a highly specialized, incredibly potent tool. It stores data as a sparse, sorted map, organizes it across a masterless ring, and handles disk I/O with absolute ruthless efficiency. If you're preparing to handle millions of writes per second, or architecting a platform for hundreds of millions of users, the traditional rules of databases just no longer apply. So, taking all of this into account, how will you design your next massive system?